So if alpha is a rational number, we have seen that the fractional parts of alpha, 2 alpha, 3 alpha, etc. is going to be a finite set. Whereas if alpha is an irrational number, then the numbers listed in 3.6 that you see in the slide, the fractional parts of alpha, 2 alpha, 3 alpha, etc. cannot be finite. Any two of these are distinct. That the list of numbers, fractional parts of alpha, 2 alpha, 3 alpha, etc. is a sequence of pairwise distinct numbers in the interval 0 to 1. And so they must have limit points. So now let us show that every point of 0, 1 is a limit point. Namely, the sequence that you see in 3.6 is dense in the interval 0 to 1. So to do that, let us begin with a simple observation that it is enough to prove that the set H equal to m plus n alpha, where m and n vary over integers, is dense in R. Observe that this H is a subgroup of the real numbers. If you take two elements in H and add them up, again you have an element of H. If you take an element in H and you take its opposite, that is, take minus of that number, again it's in H. So this H is a subgroup of real numbers under addition. Now suppose we prove that this set H is dense in R, then H intersect the interval 0, 1 would be dense in 0, 1 and our job would be done. And the intersection of H with the interval 0, 1 is precisely the number that you see in equation 3.6. The set H intersect 0, 1 is precisely the set of numbers that you see in 3.6. So let's see. It is clear that each of the fractional parts n alpha lies in H intersect 0, 1. That's very clear because look at H, it's m plus n alpha. Take the m to be minus square bracket n alpha in particular, and you see that the fractional parts do lie in H intersect 0, 1. On the other hand, if you take an element x which is in H intersect 0, 1, then x is the same as a fractional part of x because it lies in the interval 0, 1, 1 excluded, and that is going to be equal to m plus n alpha because x is also in H. So compulsorily we must have that m plus square bracket n alpha must be 0 and x must be the fractional part of n alpha. So we have verified that H intersect 0, 1 is precisely the list of numbers, fractional part of alpha, fractional part of 2 alpha, fractional part of 3 alpha and so on. Now that we have shown that our problem boils down to showing that H is dense in R, we proceed towards that goal. So we make a general observation. H is a subgroup of the real line, we have seen that. Now we shall show that H is not a cyclic group. So now let us observe that H is a subgroup of R and H is not cyclic. It is very easy for you to show that H is not cyclic. I leave it as an exercise for you to show that H is not cyclic. Now the result will follow from a general result in the next slide. So suppose you got a subgroup of R which is not cyclic, then that subgroup must be dense in R. Since H is not cyclic, H must be dense in R and our job is done. Okay, let's go to the proof. Suppose H is a non-cyclic subgroup of R. In particular, H cannot be the 0 subgroup because the 0 subgroup is a cyclic subgroup. Take an element x in H and x is not equal to 0. Then minus x is also in H, which means H contains positive elements. One of x or minus x must be positive. So now let us take the set of all positive elements in H and take its infimum. Let's call that infimum mu. Now let us show that if mu is positive, then H is cyclic and that would be a contradiction. So compulsorily mu must be 0. To show that if mu is bigger than 0, then H is cyclic, if mu is already in H, then what happens? H intersect open interval mu to mu is empty, because if it contains an element, say y, so suppose if y is in H intersect mu comma 2 mu, then y minus mu will be in H because it's a subgroup, and y minus mu is strictly less than mu and is positive, and that contradicts the fact that mu is a infimum. So immediately we see that if mu is in H, then H intersect mu comma 2 mu is empty. Similarly, H intersect open interval 2 mu comma 3 mu is empty, and so on. So we will see that H is exactly mu, 2 mu, 3 mu, etc., 0, minus mu, minus 2 mu, etc. And so H becomes a cyclic subgroup generated by mu. And our hypothesis that H is a non-cyclic group precludes this. So mu cannot be in H. Now, the next case, mu is positive and mu is not in H. Again, we are going to arrive at a contradiction as follows. Okay, so let us assume that mu is positive. Mu is the infimum, remember? Mu is the infimum, mu is positive, and mu does not belong to H, which means we can find a sequence xn of positive elements in H converging to mu. By passing to a subsequence if necessary, we may assume that xn is strictly decreasing. Every sequence has a monotone subsequence. That's a general fact. And since the subsequence converges to the infimum, it can be strictly decreasing. So take epsilon equal to mu by 2. Then there is an integer n0 such that absolute value of xn minus mu less than mu by 2 for all n greater than or equal to n0. That's a definition of convergence. Okay, so now let us take n bigger than m bigger than n0. Then what do we have? Then these numbers xn and xm are between mu by 2 and 3 mu by 2. And we have xm is going to be less than xn because we are looking at a strictly monotone subsequence. So now what does that mean? That means that xn minus xm is positive and less than mu by 2. So I got a positive number, xn and xm are in H, so xn minus xm is a positive number in H which is less than mu by 2, which contradicts the fact that mu is the infimum. So this case is also out. So now we are now left with the only case that this infimum mu is 0. So let us take this case where the infimum is 0. So now we shall show that every interval AB contains an element of H. Now since mu is the infimum and mu is 0, I can find a sequence of positive elements yn in H converging to 0. So pick a yn in H such that 0 less than yn less than 1/3 of b minus a. Take my epsilon to be 1/3 of b minus a, for instance, and this interval 0 comma 1/3 of b minus a must contain an element yn in H. Now there must be a least natural number k such that kyn must exceed a. That's the Archimedean property. And so k minus 1 yn is less than or equal to a, or kyn is less than or equal to yn plus a. So now we have got the situation a strictly less than kyn less than or equal to a plus yn, but yn is less than 1/3 of b minus a. So we got the chain of inequalities a less than kyn less than or equal to a plus yn, which is less than a plus 1/3 of b minus a, which is strictly less than b. So we have produced an element, namely kyn, which lies in our subgroup and which is also in open interval AB. And so H intersection AB is non-empty. Therefore, H is dense in R. And the job is done. We have proved that the subgroup H, namely m plus n alpha, where m and n vary over the integers, is a non-cyclic subgroup of R, and hence it must be dense in R. This is a very elementary argument, and the proof of Kronecker's theorem is complete. This is a purely group theoretical result. Kronecker's theorem basically follows just from basic group theory, but what we have proved is a very weak version. We only proved the density of the sequence of elements in 3.6. Fractional part of alpha, fractional part of 2 alpha, fractional part of 3 alpha is dense in 0, 1. what we want to do is to sharpen Kronecker's theorem significantly. In this slide, you see some exercises that I indicated which are related to Kronecker's theorem. I briefly discussed this last time, and so I'll skip this right now and move on to the promised sharpening, which is due to Hermann Weyl. It's called Wiles' equidistribution theorem. So what does Wiles' theorem say? So let us take two elements A and B which are positive, 0 less than A less than B less than 1. We know from Kronecker's theorem that this interval A comma B contains infinitely many points in the sequence 3.6 because the sequence of points listed in 3.6 is dense. So every open interval must contain infinitely many points, namely the open interval AB must contain infinitely many points. So now let us look at the first n elements in the list 3.6, namely alpha, 2 alpha, n alpha fractional parts. Now some of these will lie in the interval AB, say k sub n, that is kn is the number of points in 3.7 that lie in AB. So now let us look at kn by n. Kn by n tells you what fraction of the elements in 3.7 land up in the interval AB. Now I take n to become larger and larger. So in some sense I want to look at the limit as n tends to infinity, kn by n. Wiles' theorem says that this limit 3.8 exists and it is exactly b minus a. Just to give an illustration, let us take an interval of 0, 1 of length 1/4, namely b minus a is 1/4. Then what does equation 3.8 say? 3.8 says that approximately 1/4 of the numbers 3.6 land up in my interval AB. In other words, what fraction of the numbers listed in 3.6 land up in the given interval, and that fraction is exactly the length of the interval. So let's go further. So in this sense, Wiles' theorem quantifies Kronecker's theorem. It sharpens Kronecker's theorem and it actually quantifies Kronecker's theorem. Let us now plunge into the proof of Wiles' theorem. We shall follow the treatment in Andrew Browder's excellent book on mathematical analysis, an introduction, which is published by Springer Verlag in 1996. An Indian edition is available. I strongly recommend Andrew Browder's book for whatever mathematical analysis that you might need for your work, specifically for Fourier analysis. It's a very well written book and very clearly written book. So now let us take the characteristic function of the interval AB, namely chi of t is 1 if t belongs to AB and 0 if t doesn't belong to AB. The usual characteristic function of a set that you encounter in basic mathematics. Then what is the characteristic function of j alpha fractional part? That will be 1 if the fractional part j alpha lies in AB, it is 0 otherwise. So I want to count how many elements in the list 3.7 land up in the interval AB. What is that number? You simply count the characteristic function of brace bracket alpha, characteristic function of brace bracket 2 alpha plus etc. plus characteristic function brace bracket n alpha. So each of these summands will be either 0 or 1. It will be 1 precisely when the element brace bracket j alpha lands up in AB, 0 otherwise. So this sum is going to give you exactly kn. So what is going to be kn by n? Kn by n is going to be exactly 1 upon n times characteristic function evaluated at brace bracket alpha plus characteristic function evaluated at brace bracket 2 alpha plus etc. plus characteristic function evaluated at brace bracket n alpha. You see the displayed equation 3.9 in the slide. So you begin to see the appearance of a Cesaro sum. And so the connection with Fourier's theorem is clear now. So we got this equation 3.9. Now nothing stops us from generalizing it further. Instead of working with the characteristic function of the interval AB, I replace it by any integrable function f of x, and instead of looking at 3.9, we more generally consider the Cesaro sums 1 upon n into f of brace bracket alpha plus f of brace bracket 2 alpha plus etc. f of brace bracket n alpha, namely 3.10. This Cesaro average, you simply abbreviate it as ln of f. So what does the theorem say? The theorem says that if alpha is an irrational number, and suppose f of x is a bounded and Riemann integrable function on AB, then the Cesaro sums 3.10 converge pointwise to the integral a to b fx dx. Now what happens when I take f of x to be the characteristic function of AB? The integral is precisely b minus a, and so 3.10 becomes simply 3.11. In the limit you get b minus a, and that's exactly what we wanted to prove. That's Wiles' theorem. Wiles' theorem is exactly 3.11. So we must prove that the Cesaro sums 3.10 converge to the integral from a to b fx dx. Before getting into the proof of this, let us make two simple observations. The operator ln f is obviously linear. Ln of c1 f1 plus c2 f2 is c1 ln f1 plus c2 ln f2. Linearity is absolutely clear. The other thing is monotonicity. If f is less than or equal to g, then ln f is less than or equal to ln g. Okay, so these two are obvious from the definition 3.10. Now let us verify theorem 30 for the very special case, namely f of x equal to exponential of 2 pi I kx. I have taken a very special f of x, e to the power 2 pi I kx, and let us compute what is ln f in this case. So f of j alpha brace bracket, what is f of brace bracket j alpha? Exponential of 2 pi I k brace bracket j alpha. But what is brace bracket j alpha? It is j alpha minus square bracket j alpha. Square bracket j alpha is an integer, and e to the power 2 pi I n is 1 whenever n is an integer. Exponential function is periodic with imaginary period 2 pi I, and e to the power 2 pi I is 1, e to the power 4 pi I is 1, etc. So you simply get f of brace bracket j alpha is simply exponential of 2 pi I kj alpha, and so the Cesaro sum 3.12 is simply a finite geometric series with common ratio exponential of 2 pi I k alpha. Now let us assume k is not 0, because if k is 0 the common ratio is 1, and let us assume that the common ratio is not 1, and we know how to compute the sum of a geometric series. It's a very easy and very elementary thing, and so the Cesaro sum 3.12 when k is not equal to 0 becomes exponential of 2 pi I k alpha upon n into 1 minus exponential of 2 pi I k n alpha upon 1 minus exponential 2 pi I k alpha, and this evidently goes to 0 as n tends to infinity. That's very trivial to check. On the other hand, integral 0 to 1 fx dx is what? Integral 0 to 1 x of 2 pi I kx dx, which is 0 if k is not equal to 0. So we have checked 3.13. We have checked that limit as n tends to infinity 1 upon n f brace bracket alpha plus f brace bracket 2 alpha plus etc. plus f brace bracket n alpha equals integral 0 to 1 fx dx. The theorem has been verified for the special case when fx is e to the power 2 pi I kx. What happens when k is 0? When k is 0, the geometric series is what? The geometric series is simply 1 plus 1 plus 1 plus 1 n summands divided by n, which is 1. And what is the integral from 0 to 1 fx dx? Again 1. So the theorem is trivial when f of x is the constant function 1. So now use linearity of ln. Use linearity of ln. Now you see it in the slide. Ln of C1 F1 plus C2 F2 equal to C1 ln F1 plus C2 ln F2. And if I take linear combinations of e to the power 2 pi I kx for k equal to 0, 1, 2, 3 with real coefficients or even complex coefficients, what do I get? I get a trigonometric polynomial. So for a trigonometric polynomial, we have verified theorem 30. So we have checked the result when you have a trigonometric polynomial. Now we come to the next stage of the proof. We are going to go beyond trigonometric polynomials and go to continuous functions. How do you pass from trigonometric polynomials to continuous functions? Fourier's theorem helps us. Fourier's theorem says that if I take a 2 pi periodic continuous function, then there is a sequence of trigonometric polynomials converging uniformly to f of x. The Cesaro sums or the partial sums of the Fourier series, that's a trigonometric polynomial. It converges uniformly to f. So given a 2 pi periodic continuous function, there is a trigonometric polynomial g such that supremum of mod fx minus gx is less than epsilon for any given epsilon. There is one small change here from this situation to what we have. What we have been looking at so far are 2 pi periodic functions, and our trigonometric polynomials are linear combinations of 1 sin x cos x sin 2x cos 2x. But what we have done here, we have rescaled the variable by introducing the factor 2 pi in the argument of the function itself. We are looking at exponential of 2 pi I kx, not exponential of I kx. Thus, we are looking at sin 2 pi x, cos 2 pi x, instead of looking at sin x and cos x. Instead of looking at sin nx and cos nx, we are looking at sin 2 pi nx and cos 2 pi nx. So instead of trigonometric polynomials approximating 2 pi periodic functions, we are looking at trigonometric polynomials of the form linear combinations of x of 2 pi I kx for k equal to 0, 1, 2, 3, etc. approximating 1 periodic continuous functions. The same thing goes to this, just the variable x has been rescaled, that's all. So the above approximation theorem can be reformulated as follows. Suppose f of x is a continuous 1 periodic function on the real line, then fx can be approximated in sup norm by a finite linear combination of e to the power 2 pi I kx, where k runs from 0, 1, 2, 3, etc. So now let us bring in the epsilons. Let epsilon greater than 0 be arbitrary. Let epsilon greater than 0 be arbitrary. Then there is a 1 periodic trigonometric polynomial gx such that supremum mod fx minus gx is less than epsilon by 3, 3.14. Now using linearity of ln, let us estimate ln f minus integral 0 to 1 fx dx, add and subtract an ln g less than or equal to ln of f minus g plus mod ln g minus integral 0 to 1 gx dx plus integral 0 to 1 mod fx minus gx dx. Now from 3.14, the last piece is less than epsilon by 3 because integral 0 to 1 mod fx minus gx is less than epsilon by 3. And the first piece is also going to be less than epsilon by 3 because when I evaluate f and g on brace bracket j alpha and I add them up and I take an average, it's again going to be less than epsilon by 3. So the first and the last summands are both less than epsilon by 3. What about the middle one? But remember that we have proved the theorem for trigonometric polynomials and g is a trigonometric polynomial. And so the middle one will also be less than epsilon by 3 when n is sufficiently large. So the middle summand mod ln g minus integral 0 to 1 gx dx tends to 0, and so there is an n naught belonging to n such that mod ln g minus integral 0 to 1 gx dx is less than epsilon by 3 for n bigger than n naught. And so finally putting them all together, we conclude that mod ln f minus integral 0 to 1 fx dx is less than epsilon by 3 when n is bigger than n naught, which shows that the theorem holds for one periodic continuous functions fx. So we have proved the theorem for continuous one periodic functions. Now we shall jack it up and prove it for Riemann integrable functions.